Last time we start the concept of waves, and we start by a definition of a waves that it is a disturbance in the medium or disturbance of a function of a parameters that spread out in space, traveling from place to place and traveling. Well, you can say that it's a disturbance in space-time, considering if we're talking about gravitational waves that quite famous in a few years later. It is a disturbance in space-time of a space, and that is travel from one point to another. It's also the same concept of disturbance that in some medium or in some space and time that is traveling from one place to another. The importance is that the waves is the only way that we use to communicate. We can hear other people by means of sound wave. We can see another people by means of light, which is the form of electromagnetic waves. We can feel or the sense of touch is carried on by waves in our neurons, our nervous systems. So our sense, which is 5 senses, your eyes, your ears, your nose, your tongue, and your body sensors, using some kinds of waves in order to transform or transport information. But to determine the types of the waves that involved in each case, we separate it by 2 ways. Well, this is a topic we talked last time. Is that wave using the medium, or is that wave traveling inside the medium? If it's traveling inside the medium, it means that without that medium, the wave cannot propagate or cannot go. If it uses the medium, we set it up as a mechanical waves. And there are several types of mechanical waves that involve the one in strings, the one in air, the one in water, okay? And there is only one type of waves that is not using the medium, which is the electromagnetic waves. So is it use the medium or not? We can separate it into 2 types: the mechanical wave, which is use the medium, and the electromagnetic waves. The other way to separate the types of waves is by mode of vibration. If the vibration is transverse or perpendicular to the direction of propagation of waves, we call that a transverse wave. There are several types of transverse wave that we know of. For example, electromagnetic wave. All types of electromagnetic wave have the components of electric field and magnetic field that are perpendicular to the direction of propagation. So electric field, which is doesn't use the medium, is one type of transverse wave. A wave in the strings is a transverse wave. a shallow water waves or a tsunami is a transverse wave. Okay. For water wave, they are a little bit complicated because the water can move in both ways, both perpendicular to the direction of propagation and in the same direction as the direction of propagation. It's a complex waveform, vibration form. Another one is the longitudinal waves, which means that the vibration of the medium is along the direction of propagation. And the good examples for longitudinal waves is the sound wave and sometimes of the wave in the spring. And some types of seismic wave, which is the earthquake waves, that is called P wave or primary wave. It's a wave in the medium, in the body of the earth, and it is longitudinal. So we can separate it into two types. Okay. So we take a look at components of the waves. If we look at water waves, for examples, or the wave in the string, we see that they are look like a sine function. It has a crest which is higher than the average equilibrium point, and we have a trough which is the lowest point of the waves. So the distance from crest to crest or trough to trough, or from any 2 points of the same displacement, is called a wavelength. It's the length of a wave. The name suggests that it's the length of the wave. Beyond this point, the wave start repeat itself. So we call this one wavelength. Okay. It's a distance of one length of the waves. Now, we can define another parameters of the component, which is called a speed. Okay. Okay, the speed of the wave is the time that the crest is moving per unit time. Okay, it is a time that when wave traveling, it's traveling by some distance, and the direction of the waves this goes is called the direction of propagation. Well, we didn't call that the displacement because sometimes when you're talking about waves, the object doesn't move that way. It's only the disturbance going. So we call it a direction of propagation instead of distance. Now, the time it took for the one wavelength to pass a certain point is called the period. And it also the time that the medium complete its own vibration by one complete round. So the times that the wave is moving by one wavelength, or the times that the medium is moving by one round, is called the period. And the inverse of the period is called the frequency. because when you see that if period is the time for one wavelength to complete, to move past any certain point, the number of waves that going past the same point in 1 second is the inverse of the p. So p is the time of one wave. So the number of waves that pass in 1 second is 1 over p. So the frequency, and we use the abbreviation as f, is 1 over p, and it's the period. Now, the speed of waves, or in the direction of propagation, is a distance divided by the time. So in one period, the distance that the wave traveling is one wavelength. So we have v equal to lambda over p, or v equal to f lambda. So the velocity or the speed of wave is actually the frequencies times the wavelength, or the wavelength divided by the period. So let's bring us to our some examples. We first using something that closer to us, and possibly some of you use it right now. A mobile phone that we use now using a microwave to communicate between the phone and the center of the pole. And right now we are almost the 5Gs, the fifth generation phones, which means that we're using the higher frequency, the higher rate of modulation to send up the signal in digital signals. So we send out the information at much denser rate than the first generation. However, this mobile phone is using an electromagnetic wave to communicate between the phone and we call it the pole, or the communication center. So each phone is a transmittance of electromagnetic wave, and it is designed to use what we call this a medium, or the carrier's frequency of the phones. The carrier frequency is an electromagnetic wave in microwave region, and it has a frequencies of 2.1 gigahertz for the 3Gs. Originally, our phone is using 800 and 900 megahertz frequency. That's the 1Gs and the 2G system. But right now we are talking at 2.1 gigahertz for the 3G system, and they are planning to move to the higher frequency. So the higher frequencies means that a lot more data can be transmitted. So at this point, our phone is working at 2.1 gigahertz of electromagnetic wave, and the speed of light, or the speed of electromagnetic wave in space, is 3 times 10 to the 8 meters per second. We assuming that it's not so much different for air, but actually there's a little bit slower than 3 times 10 to the 8 meters per second. It is slower by maybe 0.01%. It is tiny fragment. What is the wavelength of the wave? So this is the question. What is the wavelength of the electromagnetic wave that we use in our cell phones? So from what given is that the frequency is 2.1 gigahertz, or it is 2.1 times 10 to the 9 hertz. Giga means 10 to the 9. So 2.1 gigahertz is 2.1 times 10 to the 9 hertz. Mega is 10 to the 6, and kilo is 10 to the 3rd. Okay. And the speed of electromagnetic wave in the air is approximately 3 times 10 to the 8 meters per second. So from the equation of speed of wave equal to frequency times the wavelength is the speed of wave divided by the frequencies. So it is 3 times 10 to the 8 meters per second divided by 2.1 times 10 to the 9 hertz. And the answers turn out to be 0.14 meters. Okay. 3 over 2 is 1.5, and 10 to the 9 divided by 10, 10 to the 8 divided by 10 to the 9, which is 10 to the minus 1. So we have 2.1, which is a little bit larger than 2. Our result is a little bit smaller than 1.5. So it's 0.14 meters or 14 centimeters. So you possibly can imagine that your phone is transmit an electromagnetic wave out with the wavelength around like 14 centimeters, around the size of a protector's ruler. So in order to describe a function of the waves, we need to have a mathematical description. So we supposed to have written the function of the wave in form of mathematical formula. So we come back to a mathematical ideas of how to represent a propagation of the waves that going to the right hand side by velocity v. Now let me make it clear here that this is not actually a solution regarding to the mechanics of waves. It is a mathematical description. Okay, it is a let's say it's a cheating way of getting that solution, instead of actually, if we take a mechanical waves, instead of solving the Newton's law of motion of the particle in the medium when it is to find the force and the acceleration and then to find the displacement. We use the comparison to get the result. However, the result is almost the same. Okay. So if we have a wave in which we say that it's a shape of a sine wave at t equal to 0 located at some point, okay, and then after one period, that wave is moving by one wavelength ahead. So you see that the end point of this wave is at the beginning of the one at initial point. So the question is, how can we find a mathematical function that can describe this, can mimic this propagation? So it's turned out to be like this, okay? Before we go into that, we will see, let me explain some of the propagation of waves, especially for a transverse wave. Let's start by assuming that at t equal to 0, the shape of the wave is like the green line. It is a sign. What actually happens when the wave traveling to the right by distance delta x is not that the whole wave, the whole function moving to the right. The function is not moving to the right in the direction of motion. Actually, the particle of the waves is moving perpendicular to it. So instead of that particle at point A moving by delta x to the right, it is actually going down. So on the left-hand side of the yellow line, actually the particle is on the green line is going down, and the particles on the right-hand side is going up. So the motion of the medium itself is perpendicular to the direction of propagation of waves. So this is how they move. Okay, and it also means that when one wave is passing through the certain point, that medium is going to complete one round of oscillation. Okay. In a way, the wave and oscillation are two things that are related. So the velocity is delta x by delta t, or lambda over p, or f lambda. But actually, the movement of the medium is in the direction perpendicular to the direction of propagation of the waves. Okay, so let's take a look at some mathematical function. Let's say that if we have any function y equal to fx, for example, y equal to x squared, this function is a parabolic function, and it is centered at the origin. So when x equal to 0, y equal to 0. When x equal to 1, y equal to 1. When x equal to 2, y equal to 4, something like that. So this is a graph of a parabolic function around x equal to 0. Now, if I write this function, but instead of y equal to x squared, I write it like y equal to x minus a squared, in parentheses and then square. This function is looking the same as y equal to x squared. But instead of staying at origin, the lowest point where y equal to 0 will be centered at x equal to a. So when x equal to a, x minus a is 0, so y is 0, so that is point. So the parabolic function is moving to the right by a distance a. And if we have y equal to x minus 2a squared, this function will also the same shape, but center at x equal to 2a. Now, if I, instead of have y equal to x minus any constant, I said y equal to x minus vt. V is the speed, and t is the time. So y equal to x minus vt squared is a parabolic function, but instead of center at 0 or any point, the center point of this graph is moving to the right as time passes. So when t equal to 0, this graph is centered at x equal to 0. When t equal to 1, this graph will center at x equal to v. And when t equal to 2, it will start by 2 v's. So this is a graph of a function that moving to the right with speed v's. Okay. On the other hand, if you have y equal to x plus a squared, you got the graph, the same graph, but it's moving from right to left. It's moving to x minus a. So y equal to x plus vt squared is a graph that moves to the left with speed v. And when y equal to x minus vt is a graph that moving to the right with speed v. So conclusion, if you have y equal to f function of x minus vt, it is a function that moves to positive x with speed v from left to right. And y equal to f of x plus vt, it is a function that moves to negative x with speed v. So in form of a wave, we see that the wave is looking like a sine function. So in one sense, if the, well, it can be looking different. It can be triangle. It can be a Gaussian. It can be any strange shapes. But as long as it has a function that t equal to 0, something like this, you can write that down in a function of x equal to x minus vt or x plus vt. So let's be assuming that for a simple waves, that is a sine function. It can be written as y equal to a sine kx minus vt. Now, why do we have the k? Because the sine function doesn't have sine of something without the units. But the x minus vt has a unit of length. So we need some constant that has a unit of 1 over length to cancel it out. So you have a sine kx minus vt as an equation for a sinusoidal wave. Sinusoidal means that the wave that look like a sine function that propagate in positive x direction, so from left to right. And y equal to a sine kx plus vt is a function that going from right to left. Okay. Now the k is called the wave number. It has a unit of 1 over meters, okay, or we call it a wave number, 1 over length. Okay. And actually the units, this k is changing from length to radian. So it is 2 pi over lambda. We can prove that. Okay. We can prove that, okay, by saying that, let's say x1 and x2 is 2 points that having the same displacement. So it have the same value for y. Okay, let me grab some things and then reset some of the, add some pages in this. Okay. for just a minute. Okay, stop share for a few minutes, and then end the show, and then we increase 2 slides. Okay, let's see. Let's say x1 let's say x1 and x2 are two places with the same displacement. So we have y equal to a sine kx1 minus vt at the same time, and y equal to a sine kx2 minus vt. So let's assume that x2 minus x1 is lambda. We already know that it is the wavelength, okay, but we can prove it here. Is the distance equal to wavelength? So we have y equal to a sine k x2 is x1 plus lambda minus vt. Okay. And then this is also equal to a sine kx1 minus vt. Now, if I multiply by k, we get a sine kx1 minus vt. Just kx1 minus kvt. So you get kx1 minus vt, and then plus k lambda equal to a sine kx1 minus vt. And by doing that, you know that sine of theta plus 2 pi is actually equal to sine theta. Or actually, this is 2n pi. It can be more than 1. So you see that for this to be true, k lambda must equal to 2n pi. And the lowest distance is when n equal to 1. So k lambda is 2 pi, or k is actually 2 pi over lambda. that the proof for Ks. You can do the same thing with the V's, and you turn out that there are omega equal to kV, and then because k is 2 pi over lambda v and then omega, we see that F is equal to omega over 2 pi. This is frequency. And omega is called angular frequency. Okay, so I use it. So here's a quick quiz. A wave has a function of y equal to a sine minus kx minus omega t. What is the direction of the waves? Now, you have to be careful with this because the minus kx minus omega t or minus vt is actually a sine minus kx plus vt. And because sine of minus theta is minus sine theta, so it's y equal to a minus a sine kx plus vt. This is the wave that moving to the negative x-axis, or from right to left, not from left to right. Okay, even though they have a negative sign in front of the velocity. So this is a general function or a general form. Okay, a general function, a general form of waves, of sinusoidal waves that traveling. For a positive x direction, it is a sine kx minus omega t, and for a negative x direction, it is sine kx plus omega t. So in this page, we are introduce the omega also. By multiply the kx inside, you get a sine kx minus kvt. And k is the wave number, so it's 2 pi over lambda. So kv is 2 pi over lambda times f lambdas. So it's kv is 2 pi f. And call this omega. It's called the angular frequency. And omega is k times v, or omega v is omega over k equal to f lambda. So this is the function. Okay. So let's take a look at the example. A sinusoidal wave is described by y equal to 0.25 meters sine 0.30x minus 40t. Y and x are measured in meters and t is in seconds. This means for these waves, the amplitude, the angular frequencies, the angular wave numbers, the wavelength, the wave speed, and the direction of motion. So by comparison, we have y equal to a sine kx minus omega t. And when we look at this equation, we see that the sign in front of the time, the t is a negative sign. So it means that this wave is traveling in positive x direction. The amplitude or the maximum displacement of the waves is 0.25 meters. The amplitude is the terms in front of the function. It gives us the maximum value of sinusoidal waves. Omega is 40 second to minus 1 or 40 hertz. So 2 pi f is 40, so frequency is 40 divided by 2 pi hertz. Wavelength or wave numbers is 0.30 meters to the minus 1. So k is 2 pi over lambda. equal to 0.3. So lambda is 2 pi over 0.3 or 20 pi over 3. Now, to find the velocity, you can use the v equal to f lambda, or you can use omega v equal to omega times k. Kv equal to omega. So v equal to omega over k. So it is 40 hertz divided by 0.3 meters to the meters to the minus 1. So it's 400 over 3 meters per second, or velocity of 133 meters per second, which is rather fast for the wave. Or you can use v equal to f lambda. So it is the same result, 400 over 3 meters per second. So this is quite a fast wave. And the only things I can think of, the natural representation of this wave is the tsunami waves. Its travel, this is still half the speed of sound. So it's regardless, it looks like the tsunami. Okay, 133 meters per second. Is about 479 or 480 kilometers per hour. That's in the range of a tsunami wave. And because the phase is kx minus omega t, the minus sign tells us this direction of propagation is a positive x direction. It's from left to right. Okay. So 11:27, 25. We can still have about 15 minutes to go. So let's spend some time on this question. A mathematical expression for the wave is given by y equal to 0.5 meters cosine of 0.3x plus 60t minus pi over 2. Find the amplitude, the wavelength, the frequency, and speed of wave, direction of motion, and the displacement at t equal to 0 and x equal to 0. So I will give you 15 seconds for each problem. 1 and 1.5 minutes to work this problem. Write down your answer and we will see the solution afterwards. Okay, I will pause the lecture for 2 minutes. Okay, let's get back to this question. The amplitude is 0.5 meters. The wavelength, we know that the wave numbers is 0.3 meters to the minus 1. So let's add these things a little. It has a minus 1 here. So 2 pi over lambda is 0.3. So lambda equal to 2 pi divided by 0.3 or 20 pi over 3. Frequency omega is 60 hertz. So the frequency is omega divided by 2 pi. So it is it is 30 over pi hertz. Now the speed of wave is omega over k, so it's 60 over 0.3 or 200 meters per second. Also a tsunami waves. Or you can do the f lambdas to yield the same results. Direction of motion, because in front of the time, it is a positive sign, so it is a negative x direction. And the displacement at t equal to 0 and x equal to 0, this is what I want you to see. You see that when x equal to 0 and t equal to 0, it is a 0.5 meters cosine of minus pi over 2. And cosine of minus pi over 2 is actually 0. Pi over 2 is 90 degrees. Cosine of negative 90 degrees is 0. So the displacement is 0, even though it is a cosine function. So actually this space can be written by a 0.5, negative 0.5 meters sine of 0.3x plus 60t. Okay. Here, because cos theta minus pi over 2 is sine theta. So sine theta minus pi over 2 is minus cosine theta. So it is actually y equal to 0.5 sine 0.3x plus 60t. It is a, take a look at this unit circle. You have an angle theta, and then you subtract by pi over 2. Okay, so this is the angle of theta minus pi over 2. Then you see that the sine of theta minus pi over 2 is minus cosine theta, and cosine of theta minus pi over 2 is actually a sine theta. Okay. So we get back to this, the speed of wave. As I told you that these two examples have a very fast wave, 200 meters per second, or 133 meters per second, almost 500 kilometers per hour. Okay, it is a special kind of waves. What actually happened is that the speed of wave in the medium is a function of a physical properties of a medium. For example, electromagnetic waves of in space or in vacuum always have the speed of 3 times 10 to the 8 meters per second, regardless of their frequencies and their wavelength. However, when electromagnetic waves or light traveling into a medium, for example, air or water, it slows down. So the speed of wave in any types of medium is depending on the physical properties of the medium. For example, another example is sound wave. The sound wave in the air is approximately 350 meters per second. However, if you create the sound wave in water, it turns out that the sound wave in water can propagate at 1500 or 1500 meters per second. And if you're going down and create a sound wave in the ground or in rock or steel, for example, you hitting a pipe, you hear the sound in the air, and there is a sound that propagates to the pipe, and that is traveling at almost 3000 meters per second or 3 kilometers per second. So in different mediums, it have different speeds regardless of their frequencies and their wavelength. So this V equal to F lambda. This velocity is depending on the physical properties of the medium. So as long as you stay in the same medium, that velocity remains constant. For electromagnetic waves, okay, we see that the vacuum has a speed of 3.0 times 10 to the 8 meters per second. In water, it's slowed down by a fraction of n. N is what we call an index of refraction, because it has some things to do with the refraction of light. This n is always greater than 1. So in water, n is approximately 4/3 or 1.33. So the light in water is slowed down by a fragment of 1.33. So we can take a look at this. For a medium of vacuum n equal to 1, that's an exact value. So the velocity is 3 times 10 to the 8. For the air, the index of refraction is 1.000277. So that means it is a little bit, a tiny fragment greater than 1. So the speed of light in air is slightly lower than 3.0, but we can approximate that it is the same because it is at fourth decimal different. For ethyl alcohol, it is 1.36. So the speed of the light in ethyl alcohol is 2.2 times 10 to the 8. For water, it is 4/3 or 1.33. So the speed is 2.26 times 10 to the 8. For glass, it is between 1.25 to 1.75. Fused quartz is 1.45 and crown glass is 1.485 to 1.75. This is depending on the density of the glass. Okay. And diamond, which is the, I think is the highest transparent materials of highest index of refraction we have now. It is 2.42. So the speed of light in diamond is 1.23 times 10 to the 8. So this is quite the lowest speed that we have. Actually, there are some other materials that is having higher index of refraction than diamond, but it's the thing is it is not transparent. Okay, so the electromagnetic wave get absorbed in that type of materials. Now for sound wave, I'm not going to prove it for you. We're almost there. The velocity of sound wave is square root of b over rho, and b is a constant called a bulk modulus of the medium, and the rho is the density. So from this look, you might think that the bulk modulus is constant, and therefore the velocity is inverse proportional to the square root of density. Which means that the higher the density, the lower the speed of sound. But it's on the other hand, the bulk modulus itself is a function of density. So the higher the density, the higher the bulk modulus. So a water which has a higher density than the air also have higher density than bulk modulus than the air. So it turned out that the velocity of sound in water is much higher. So let's take a look at this, some of this value. For medium, water have bulk modulus of 2.2 times 10 to the 9th. The unit of bulk modulus is Pascal or Newtons per square meters. And density is 1,000 kilogram per cubic meters. And finding the velocity give 1,483 meters per second, or roughly 1,500 meters per second. For steel, it have the bulk modulus of 160 times 10 to the 9th Pascal. And density is 7 times higher than water, 8 times 7.8, 7,800 kilograms per cubic meters. So the velocity of sound in steel is 4,529 meters per second. Now the air have bulk modulus roughly equal to the atmospheric pressure times a constant. It is 1.42 times 10 to the 5th Pascal. The density is 1.29 kilograms per cubic meters. So it's reduced by almost a 10,000 times. So it turned out to be 331 meters per second. You see that bulk modulus is also density related. Now, for the air, we have some things that quite interesting, because the bulk modulus in the air using thermodynamics, which is you will learn in the second half, you will see that the bulk modulus is gamma times T0, and gamma is called a diametric constant. For the air, it is 1.4. It is a constant. T0 is the pressure at that point. For atmospheric pressure, it is 1.013 times 10 to the 5th. However, this pressure is different by terms of temperatures. According to gas law, T0 is rho times RT over MA. MA is the molecular mass of the air. You can say this is constant. So you will see that plug in the P0s into this, you got bulk modulus is gamma rho R over MA times T. And then you divide by the rho and the rho is canceled. So the velocity of the sound in the air is actually a function of temperatures. Gamma is constant, R is constant, MA is constant. So in the air, the actual velocity of the air is proportional to square root of temperatures in Kelvin. And we can, using this, V over V0 is square root of T over T0s. And V0 is the speed of sound at 30 degrees Celsius, which is 331 meters per second. You can prove that, but I'm not going to prove it here. So at 27 degrees Celsius or the 300 Kelvin, the velocity or the speed of sound in the air is V0 times square root of 300 over 273. And it gives you 347 meters per second. Okay, yes, and it will start right now. So I will just conclude it here. Will the entire wave topic be in the midterm? We will decide tomorrow how far we go on the wave topics. Okay, because this PowerPoint is 139 pages long, so we cannot include everything into 2 hours. I will see how far it goes, and then I will decide about the question later on Thursday. So let's get back to our quest.